if you look at the denominator, x plus 1 and x plus 3, that's your vertical asymptote, right? -1 and -3, that's your vertical asymptote. Now, in calculus, we call that discontinuity. Why discontinuity? Because at that point, the function being abrupt, there will be a gap, right? It's no longer smooth. You put your finger across the graph, it cuts your finger because it's being abrupt. So at those points, we call them discontinuity in calculus. Now, there are two types of discontinuities. There's one type that you cannot remove. It's remain there. And that's where you see the vertical asymptote. That's where the graph going either shoot up to positive infinity or drop down to negative infinity, right? The other type is removable discontinuity. That means you can remove that point where make the graph undefined, and then you can stitch the graph together again, right? So no longer a gap. Right? It's kind of there was a break, and then now you can stitch it back again. If you can look at this function, I can cancel what? X plus 1 and x plus 1, right? So those points right there, where you can cancel, those called removable discontinuity. You'll be able to remove it from the graph, and then the graph coming back together again, right? That's what removable discontinuity is in formal definition. Of course, in calculus, they give you a formal definition. But right now, that's all you have to understand. A removable discontinuity occurs when graph of the rational function at x equal a, here is x equal -1. If the factor x minus a to the n power, here the factor is x plus 1 to the first power, right, occurs in both numerator and denominator, hence you can cancel it, hence removed, right? The value a is excluded from the domain. Now, if I ask you what is the domain of that function, you would look at the reduced function, right? So reduced function will be x minus 2 over x plus 3. Right? So you're gonna look at that red function to tell me what's the domain, right? In this case, it will be everything except -3. Now, how do I find the removable discontinuity? Let's take a look at example A. I'll go through step by step from 1 to 3. Step 1, first, you're gonna factor the numerator and the denominator in factor form, like they did right there, right? Actually, we have to do more. The top is okay, but the denominator for x minus 1 quantity square, I can write it twice. Right? So you're gonna factor into irreducible factor. So x minus 1 times x minus 1. So I can see that you try. What can you cancel? X minus 1 of the x minus 1 on x minus 1 on the top, and 1 of the x minus 1 in the denominator. So now your reduced function will be x plus 3 over x minus 6 times x minus 1. So once you factor the numerator and denominator, if the common factor remain in the denominator, there is a vertical asymptote. So here in my reduced function, the vertical asymptote will be x equals 6 and x equals 1, right? Because it's remained in the denominator.
The rest of x equals -2 centimeters.
Oh, minus.
So you would say, so VA, vertical asymptote, is x equals 6 and x equals 1. Since it's remaining in the denominator after the cancellation. Is there a discontinuity? Is there a removable discontinuity? It was, right? It was. It was the x equal 1 was my removable discontinuity. But the problem is that you only have 1 on the top, but you got 2 on the bottom, right? So x equal 1 remain vertical asymptote, right? So here, so conclusion, there's no removable discontinuity here. You only be able to remove 1 of them, but there's still the same 1 left over in the denominator. Oh, that example is making me confused. Maybe the next one better. Well, I didn't pick the problem. So you would say since factor x minus 1 remains the denominator, thus imply x equal 1 is still a vertical asymptote. And the reason because there are 2 of them in the denominator. Hypothetically, if it was just 1, if it's just 1 x minus 1 each, then yes, x equal 1 will be your removable discontinuity. What is the domain for this problem? Everything except 6 and 1, right? Everything except 6 and 1. So I'll draw it out like this. 1 come first, and then 6. It doesn't matter the scale as long as you put the number in the right order. Because I don't take 1 and I don't take 6, I'm gonna put this hollow circle around them. And then if you look at the function, everything except 1 and 6. So in integral notation, your answer will be what? From negative infinity up to 1, right? And then union from 1 to 6, and then union 6 to infinity. It's helpful if you be able to put it in a number line. And all you do is just dodge the point that you don't want to be included, right? So far, so good. Zoomer, if you have any questions, please ask. Okay, I don't feel like I don't want you feel like you're being left out. You can either speak it out loud or you can put your answer in the chat. 1B, they already factor for us. It's the same problem. The only difference is x minus 1 is linear. It's not quadratic. So here we can cancel the x minus 1 on the top and the x minus 1 on the denominator. So my reducible function will be x plus 3 over x minus 6. Is there a removable discontinuity? Yes, right. In this way, x equal 1. So yes, you say I would say x equal 1 is a removable discontinuity. Sometimes they call that a hole. When you have a hole on the graph, you'll be able to remove it. But when you have a vertical asymptote, when you have like a big gap, there's no way you can fill in that gap. All right, so we found a removable discontinuity. The problem is you only found the x coordinate. I want a point. A point means I need x coordinates and y coordinates, right? So all I have to do is plug in x into the reducible function. So what we're gonna do is we're gonna plug x equal 1 into I'm gonna call reducible function star into star. So I don't want to rewrite that. So you have g of 1 now. This is g of x equal 1 plus 3 divided by 1 minus 6, which is negative 4/5. Negative 4/5 is equal to negative 0.8. But usually I prefer the fraction. It doesn't, actually, let me rephrase. I prefer the exact values. In this case, both negative 4/5 or negative 0.8 are exact values, so it doesn't matter. So 1 negative 4/5, or you can use negative 0.8. That is the removable discontinuity or the whole. Let me show you what it looks like in decimals. I hope it's I should have restart my my iPad. I'm sorry. I should have restarted my iPad. Look at that. It just. All right. So right there, you can see. That's the hole right there. You can see the little dot. I don't know if you can see it. Yeah, the little dot right there. 1 negative 0.8. Okay. Should have started the iPad. All right, so that's removable discontinuity. Now we're gonna graph rational function with removable discontinuity. So one more thing added to the graph. Here's big F of x. They already factor for us. By the way, on the exam, you're supposed to factor it yourself. Out of the bat, you can simplify 5x minus 5x minus 5. So that's become negative 2x divided by x plus 4. And yes, we did simplify the function. Is there a whole or vertical asymptote? What is a whole? Yeah, x equal 5, right? So you say there is a whole. And then the whole is x equal 5. Of course, that's only one coordinate. You're gonna find the y as well. So all you do is plug in. I'm gonna call this star again. I'm gonna plug x equal 5 into star. So f of 5 equal negative 2 times 5. It's lagging. Thing is the internet. So I got negative 10 over 9. That's roughly negative 1.11111, all of that. Of course, I don't, when you have something like that, I prefer negative 10, 9, right, for the point. But when you graph, of course, you look at the decimal, right? So 5 comma negative 10 over 9. That is the whole. What is the VA? Very good. x equal -4. Please say x equal -4. Don't just say -4. Find the intercepts. So that's the easy part. Let's find the y-intercept first because that's easy. Y-intercept. You know the rule. You set x equals 0. Because y-intercept, you have no width. If you plug it in, 0 divided by 4, which is 0. So y is 0. So 0, 0 is your y-intercept. I bet you 0, 0 is also x-intercept when you see something like that. Because there's 0 at both values. To find the x-intercept, you already know the answer, but just let's follow the procedure. Set y equals 0. When y equals 0, I mean -2x over x plus 4 equals 0. And I told you when you have one fraction on the left and then the right hand side is 0, all you have to do is set the denominator equals 0, right? Because the bottom cannot be 0. Always factor form. Yeah, you always. The star. Yeah. Oh, once you factor, focus on the factor form, okay? Now, it's not wrong if you go back to the original. You could have the same answers. It's just more computational things for you to do. That's all. You can use either, but I prefer reduced form because you're gonna get the same answer with less work. So -2x equals 0. Divide both sides by -2. Well, 0 divided by anything is still 0. So x equals 0. So 0, 0 is also your x-intercept, like I said. Find the VAs. Well, we found it in part A, right? So we know that x equal -4. You gotta remember the behavior. I have to consider what from the left and from the right of that book of the asymptote value, right? So I only have one value here. So what I'm going to do is I'm going to put the -4 down. I need two of them because this is -4 from the left and then -4 from the right. Remember what's next? We do test point, at least the steps in that part. They might not be able to give you. I would pick something near the value. So someone pick me a value to the left of -4. -0.9. To the left, -4.1, right? To the left. -4.1. And then -3.9 be to the right. So and then what do? You plug into that reduce function, right? You plug into -2x over x plus 4 to see the sign. You can use your calculator or you can just eyeball it. So plug in -4.1 in here. -2 times -4.1, that's positive. So positive. And then -4.1 plus 4 is negative. I have positive on the top and negative on the bottom. So my final sign will be negative. That's imply y approaches to -infinity. Remember test point function and then where y approaches to? And then when you plug in negative 3.9 into here, negative 2 times negative 3.9 is positive. Negative 3.9, my plus 4 is positive. So I have positive, positive, that's positive. So that implies y approaches positive infinity. So that's okay. Phi HA. Someone remind me, how do I find HA? Yeah. Mhm. Good, good. I understand what you mean. Yes. It's easier to just write it down than just to say it out loud, right? So let me recall you how to find HA. If you guys forget, recall to find HA. It's gonna be the leading term of the numerator divided by the leading term of the denominator. By now, I expect you to know when I say leading term versus leading coefficient. Leading term is what? The whole thing, right? Leading coefficient is just a number in front of the x. Okay. So be careful. Here, what is my leading term? Look at the reduce. It doesn't matter where you look, really. You can look at the reduce function or the original. It doesn't matter. Yeah, 2 for 1. So I'm just gonna work on my reduce function. Period. So I'm not going back and forth, making you confused. So be negative 2x divided by x, which is negative 2, and that is your y equal negative 2. And to determine whether the HA cross the graph or the graph cross the HA, you set the reduced function equal to negative 2. Right? So you set negative 2x over x plus 4 equal to negative 2. What is my LCD here? Yeah, thank you. X plus 4. Usually I like to say x plus 4 over 1. And then negative 2 over 1. I like to put things like that. It's just to give me a visualization of what is the top, what is the bottom. And then you distribute the x plus 4 into each of those. On the left hand side, x plus 4 cancel. So it's just negative 2x. Did I say left or right? On the left hand side, cancel. On the right hand side is negative 2 times x plus 4. Negative 2x equal negative 2x minus 8. If you add 2x both sides, yeah, cancel, right? So it's just 0 equal negative 8, which is false, So no crossing, no crossing. All right, all that work now is the graphs. This is the same thing we did last time. The only thing extra is the just removable discontinuity. That's all. I suggest you plot the point first, and then the vertical asymptote and horizontal asymptote. Right? Do the easy parts first. 5 and negative 10, 9. 5 and negative 1.11 something. So right here, that's my removable discontinuity. What else? 0, 0, that's my x and y intercept. That's it. And that's it. And now the vertical asymptote, x equal -4. Horizontal asymptote is y equal -2. For the vertical asymptote, I want a semi solid. All right, I think we've done the easy part. We've done the easy part. Now the behavior. The behavior will be your last, right? So at x equal -4 from the left, the function dipping down to -infinity. So I call this block. I have one block here, the other block here, and the block and block. I call them block, right? So when you see -infinity, you want to choose the bottom block, right? But like, why don't I start here, Mimi? Because if you do, you're gonna cross the AJ, right? So start there. I'm just gonna do a graph just to give me a direction of my graph. That's all. You come back and do it later. At x approaches -4 from the right, function shoot up to positive infinity. So going like that. But let's graph them properly. On the left block, it's pretty smooth, right? Everything is just kind of like that. And please do not curve this down, right? It's the horizontal asymptote. The graph gonna try to approach close to it. If anything, it's kind of go up, right? It just never reach it, but it's trying to get very close to it. On the right hand side, on the other block, it's going up, and I have to go through the 2 points, right? That Can someone tell me what's my domain? By just looking at the graph. So you go from what? You start from what? Remember, domain is going to be your x value. So it looks like the function start from -infinity, right? You just stretch this out, and then it's kind of stopping right where -4, right? So -infinity. Do I include -4? No, right? That's your vertical asymptote. And then union, another part, is go to from the right of -4, it go to infinity. Does it make sense? You don't have to look at the graph in order to tell what is the domain. You can look at the reduced function, right? Anything but -4, which is telling you right here, everything but -4, right? One is number 3. Let's see. Let's see again. I want you guys to perform the division, this one, number 4, using the synthetic division. In the meantime, I'm going to restart my laptop. I'm sorry, my iPad, so I can show you the decimals. Very good. Yeah, work. All right. So let me show the graph for the we just recently did to make sure that it's correct, right? So right there, the graph, the vertical asymptote and your removable discontinuity. So we got it right. We got it right. Now I know that you can graph it, but I suggest you do by hand first, okay? Because it's gonna be the same thing on your exam. Very much likely, we don't spend 2 lectures just going over these for nothing. What do you guys have? So you write out the. You write down. Technology is great when it works. All right. All right. 3, -3, 1, and the box will be +5. Right? Bring down the 3. 3 times 5 is 15, and then the -3 will be +12, and then 30. I'm sorry, 12 times 5 is 60, 61. 61 is your remainder. Still lagging. So you have a quotient which is 3x plus 12 plus 61 in the form qx plus rx over dx. Now, why am I doing this? This is the recall of the synthetic division because we're going to use it soon. Next, we're going to learn about the Slant asymptote. So far, we know what vertical asymptote, which is the graph never crossed, right? Horizontal asymptote, which the graph may or may not cross. And then last one will be the slant asymptote. How do I graph the slant asymptote? So that's later, but let's graph this one. I have in x-intercept is 3 and -7. The y-intercept is 0, 5. My slant asymptote is 1/2 x plus 3. By the way, slant asymptote always in linear form, mx plus b. And you guys know how to graph a linear function. You only need 2 points. So my y-intercept is at 3. So I'm gonna graph it using rise over run. And then 1/2, I'm gonna rise 1/2, right? There's my second point. Again, in reality, you don't see the slant asymptote on your graph. It's something the graph doesn't cross, so I had to put it in dashed line, so we know to not to touch it. Vertical asymptote is x equal 2. All right, now we do the behavior. As x approaches 2 from the left, y go to positive infinity. 2 from the left, 2 from the left. So this side is go to positive infinity. So it's kind of like that. As x approaches 2 from the right, y goes to negative infinity. So that's the direction. Now, let's do a proper graph. On the left, you kind of go through those 2 dots, right? So your graph looks like this. And on the right, you're gonna go through that 3, 0, the x-intercept. Direction. There you go. That's your graph with the slant asymptote. Let me introduce you more about slant asymptote. What is it? What is it? Now, last time we know how to find the horizontal asymptote using the leading term of the coefficient, leading term of the numerator divided by leading term of the denominator. Right? If the leading term of the numerator of the degree of the numerator is less than the degree of the denominator, then your horizontal asymptote is y equals 0. We talk about that. Right? If they equal, then your horizontal asymptote is equal to the quotient of the top divided by the quotient of the bottom. What happens if the numerator degree is just larger than the denominator's degree? Remember what I said last time. There's no horizontal asymptote, but there will be a slant asymptote. So that will be the third case. I use black here. Third case. I don't like they use the notation here. R of x. R stands for rational, but it's also stand for remainder. Right? So this R here is different than this R you see here. It's just confusing, right? The first one right there you see is the remainder, and this one here, the R here, is a quotient, is the rational between the top polynomial divided by P divided by Q. But yeah, the polynomial divided by the quotient. Yeah, don't worry about the notation, okay? All you have to know that your slant asymptote will be the linear quotient. That's all. That's all you have to know. Notation confuse you. So in this case, my slant asymptote will be this one right here. One more thing, slant asymptote always in linear form. So your quotient should be in linear form. If it's in quadratic or cubic or anything big, then it's not slant asymptote. Right? So you don't have a slant asymptote. How do I find a slant asymptote? Well, we did the synthetic division for region. Right? We're gonna use the division, and then the equation of the slant asymptote is the quotient of the division without the remainder. And that quotient has to be in linear form. It's always a line, so it has to be in linear form. We do one more and then we call that a day. There's number 7, that's your due types. 2. Let me write out you try 2 before I forget. 2. Then that'll be our last problem for today. Find the intercept. I always start with the y-intercept, so it's the easier of the two. Set x equals 0. When x equals 0, y is -5 over -3, which is 5/3. So 0, 5/3. And then your x-intercept, you set y equals 0. Here you gotta solve. So I'm gonna use a factor form, okay? I'm gonna use a factor form. X minus 5 times x plus 1 divided by x minus 3 equals 0. This is the same thing as x minus 5 times x plus 1 equals 0. Well, if two numbers multiply is 0, one of them, at least one of them is 0, right? So either x equal 5 or and x equal -1. So I have 5 comma 0 and -1 comma 0. You guys see that y? You see that y is your x-intercept is your numerator? Remember we did last time? We tried to construct a function using information. So x-intercept always your numerator. What is my VA? 3, x equals 3. On the exam, don't lose this. At least you have something. I don't think you can leave this blank. I don't know how you leave this blank. At least you know something, right? You don't have to, if you don't know everything, at least you know something. And the behavior near the vertical asymptote. So let's do this. You only have 1. So you need 3 from the left. And then 3 from the right. Do you know the deal? Test point, right? Test point. TP. Something from the left of 3 will be, yeah, 2.9. Thank you. And then something from the right of 3 will be 3.1. Thank you. And then you plug into the factor form. It's just easier. Right? So the factor form, let me write down here, x minus 5 times x plus 1 over x minus 3. Let's see, you can do 2.9 minus 5, that's minus. And then plus, so minus on the top. And then 2.9 minus 3, that's minus. So minus on the bottom, so becomes positive, right? And down here you say y approaches to something. In this case, approaches to positive infinity. 3.1 minus 5 is minus. And then positive. So minus positive, that's minus. In the bottom, 3.1 minus 3 is positive. So minus and positive is minus. Find the equation of the Slant asymptote. Synthetic division, right? Synthetic division. So write out the coefficient. Coefficient will be, I'll use, will be 1, -4, -5. Now you go back to the original. You don't want to use the factor form now because you're doing division. And then 3 on in the box. Oh yeah, I have. Thank you. I have it that way. Whatever I say last, I should remember it. You know, teaching higher math is easier than undergrad math because it's a lot of behind the scene kind of thing. 1 times 3 is 3, -1, -3, -8 is your remainder. So your Slant asymptote equation will be y equal x minus 1, right? X minus 1. Now we graph, then it'll be done. So let's plot the point first. 0, 5 third. 5 third is roughly 5 divided by 3 is 1. 20 divided by 3 is 6. So roughly 1.6, right? So is this one roughly 1.6? That's the y. So right here. And then 5 and -1 for x axis. Vertical asymptote is x equal 3. There's no horizontal asymptote because there's, why there's no horizontal asymptote? The degree of numerator is bigger than the degree of denominator. But that will be the Slant asymptote. So x equal, y equal x minus 1. Rise over runs again. So -1 is your y-intercept. How many units I rise? How many units I run over? 1, 1, right? So 1, 1. For the exam, I suggest you bring ruler with you, because for these kind of graph, it's helpful if you be neat. For a quadratic, then easy. There's not too much things going on there, but this graph is a lot of things going on. Behavior. When you approach 3 from the left, the function goes to positive infinity. And it has to go from the left, from the left. Okay? And it has to go those, let me just do the direction first. So like that. And then when you approach 3 from the right, it's go to negative infinity. Like that. And now a proper graph. My left block, I have to go through those 2 dots to 2 points. And then for the right block, I gotta go through that red point. Question for you, is there a removable discontinuity here? Is there any cancellation? No, right. So how you feel about rational function? There's a lot going on, right? But all you do is just look at the function and just answer the question they want you to answer. Don't think too much at once. If nothing else, see you again on Friday.